I'd really appreciate that. Okay, thank you very much. All right, so basically, please remember that you are writing a semester test soon. And so on Tuesday, all the content that you needed to cover for the semester test was covered, right? So remember, on the Tuesday lecture, Prof. Coulter did mention that the scope of the semester test basically goes up to everything that was covered until Tuesday, right? So from now on, we are doing new content, right? But this content does not apply to your first semester test, right? So we are just continuing with the content. And then next week, we will be doing revision and so basically like we'll be revising like past papers and so forth, right? Ideally, I think like we'll be doing revision during tutorials, and then we'll use lectures to continue with the content, but it might change, so just please attend all your classes and all your tutorials, because you have to anyway. Like the tutorial, remember, you only have to attend one tutorial per week, right? But do attend everything that you have to attend in case we do continue with new content. All right, so that's that with the announcement. So basically now we started with polymorphism, and this is a very important concept in object orientation, right? Because it actually allows for objects to basically behave, or rather, it allows for functions in certain classes to behave differently based on which instances we are looking at, right? So for example, like we're able to create functions in such a way that like if we allocate memory for a certain kind of class that inherits from a parent class, then that function will behave differently. And that is the whole idea behind polymorphism, right? It allows a type to basically morph into different behaviors based on the instance of that base type or general type. All right, so, and the main feature, or rather the main idea, or the main way in which we implement polymorphism in C++ is through virtual functions, right? So during the tutorials this week, you were exposed to virtual functions, and you were also exposed to pure virtual functions, right? And remember, a class that has a pure virtual function is also referred to as an abstract class, right? And the whole idea behind virtual functions is that they implement late binding, right? So the difference between early binding and late binding is that so with early binding, that's what we've been doing so far, right? So that's when you create a class, and then you create a function, and then you create a definition for that function in the CPP file. And then what your compiler does is that during compilation, it will then take the classes, rather the function prototype, and then it will bind it to the implementation of the function during compilation, right? So that happens during compilation, right? And then whenever you call that function for that particular class, or that particular instance of the class, then that implementation will be basically executed, right? So in terms of virtual functions, we have something called late binding, right? And the idea behind late binding is that a function prototype is only bound or linked to an implementation only when that function is used, right? So for the first time in code, when that function is actually called, then at that time, that function prototype will be linked to an implementation, right? So it might seem like the same thing right now, but it's actually not, because with late binding, the compiler actually waits to see which implementation from which instance is being called, right? So if, for example, you have a parent class and then you have two base classes, and then both base classes provide different implementations for the virtual function. Then when you call when you allocate memory dynamically during execution, let's say using a pointer, for example, and then you call that particular function, right? Then because that function was virtual, right? Because it's a virtual function, then your compiler is able to link that function prototype with that instance that you called at runtime, right? That is the basic idea behind late binding, right? So then we'll be looking at implementing virtual functions. We'll be looking at when to use a virtual function. We'll be looking at abstract classes and pure virtual functions. As I mentioned, if a class has a pure virtual function, then automatically the class is an abstract class. It means that it can't be instantiated, right? Because it has a pure virtual function. So you can't create an instance of that class. And then we'll be looking at pointers and virtual functions. We'll be looking at extended type compatibility. So what this means basically is that we'll be looking at how we are able to use the base type and actually make a base type pointer point to different kind of derived types. And then we'll look at downcasting and upcasting. We'll look at C++ under the hood with virtual functions. So I doubt we'll finish this set of slides today, but obviously if we don't finish, Prof. Coulter will carry on from where I stop or where I finish off. So an abstract class is one that will never call a constructor. Yes, so an abstract class can be instantiated. You can't create an instance of an abstract class. It doesn't make sense to create an instance of an abstract class because it doesn't have, like, not all the functions in that abstract class have definitions, right? So it can have a constructor. An abstract class can have a constructor, but that constructor will only be called when you create an instance of a derived class. So when you create an instance of the derived class, which derives from the abstract base class, then the abstract base class's constructor will be called. So it can have a constructor. It's just that you can't create an instance of the abstract base class. Okay, so then polymorphism is used basically to associate many meanings to one function, right? So you might have realized this in tutorials as well, right? When you create a virtual function, then based on like which instance you allocate memory for, that function, that implementation of that instance will then apply to that virtual function. So virtual function provides this capability, and this is a fundamental principle of object-oriented programming, right? It's very important with regards to object orientation, because it means that we have something called future proofing, right? Because it means that I can create a class today, and then I can create a virtual function for it, and then in future, anyone can create a class that inherits from this class, and then they can have their own implementation of the virtual function, and then I can be assured that my class will support that class's implementation. Okay, so the whole idea behind virtual is that it exists in essence, but though not in fact, right? So it's there, but it's not really there, right? It's not concretely there. That's the whole idea behind something virtual. And then so a virtual function, then by this meaning, we can think of it as a function that can be used in quotation marks, right? So you can call it before it actually has a definition or an implementation. Okay, so that is why your code is able to compile, right, before it can actually find a definition for the virtual function. So an abstract class is used to extend to other classes. If I'm saying it correctly, yes, that is true. So an abstract class is basically used as a general like base type, right? And you'll actually see with this example that we're going to go to here, right? It's basically a general base type, and then but which has to be inherited from by other derived types, which will then have more concrete implementations of the virtual functions in the abstract class. All right, so so is this the same as passing a function as a parameter? No. So that is different. Abstract classes are basically the same as like normal base classes. The only difference is that they contain a pure virtual function. Okay, so let's look at this example. So we have classes of several kinds of figures, right? So we have rectangles, we have circles, we have ovals, etc. And then, so each figure is an object of a different class, right? And that is true, right? A rectangle is a rectangle. We have a class rectangle. And then a circle is a circle. An oval is an oval, right? And then let's look at the data inside of the rectangle. So in a rectangle, we have height, we have width, and then we have a center point, right? So, and then we'll use this point to basically place the rectangle, for example, let's say at the center of a screen, right? So actually, let me just do this. I think it would be easier to explain this with diagrams. Okay, but like I'll do some drawing later. And then we have a circle. And then the data for a circle is basically its center point as well. So a circle also has a center point, and then it has a radius, right? So what makes a circle different from a rectangle in the context of what we are looking at here is that a circle has a radius, but a rectangle has a height and a width, right? But what makes them similar is that they both have a center point, right? Okay, so then a circle and a rectangle, they all derive from one parent class, which is figure, right? Okay, so now we have this class, which is figure, and then now we want to draw a figure. So we're going to have a draw function inside of the figure class, right? And then the draw function will have different instructions for each figure, right? So depending on what we want to draw, the draw function will then implement different code, right? Or rather, like it'll have maybe some sort of an if statement or something like that, depending on what figure we want to draw, right? So that is all nice and great, right? So that means, but obviously, if the figure, if this function, right? If this function must have different instructions depending on which figure we want to draw, then that means this class must know about the different figures, right? So if we only have a rectangle and a circle, then it means that in the figure class, somehow we must make this class know about a rectangle and a circle, right? So that when we call this function, we can, for example, pass a parameter and then say that draw a rectangle or draw a circle or something like that, right? So we must have a way of telling it what to draw, right? And then based on what we are telling it, then it will draw a particular figure. Okay, so then each class needs a different draw function, right? So if we were to inherit the draw function from figure, right, then we would then give obviously like a different definition in the rectangle or the circle, right? So, for example, if we want to call the draw function from the rectangle, then we would be able to call it like that, and then we would only have the implementation for the rectangle. And then if we wanted to call the draw function for the circle, then we would have the implementation for that, right? So then what we can do, for example, is just plain function overriding, right? We'll create a rectangle, inherits from figure, and then it overrides this function, and then it has its own implementation for drawing, right? So then that's still fine. That's still, there's nothing new here, right? This is just basic inheritance. Okay, but now let's say this function this class figure has another function called center. And then the function center, let's say it applies to all figures, right? So so let's say the function center basically moves the figure to the center of the screen, right? So basically, then what it would do, let's say there was a figure that's here, and then we call the function center, then its task would be to basically erase this figure. So it would erase it first. So it would erase everything in the screen, make sure that the screen is empty, and then after doing that, then it would draw that figure in the center of the screen, right? Okay, but now, so it erases first, and then it redraws. So then that is fine. But so figure center, right, which means that the center function which belongs to figure would then have to use draw to redraw, right, the figure, right? Remember I said it's going to erase a figure from somewhere and then draw it somewhere else, right? But then in order to do that, we have to call the draw function, right? So then which function do we draw, right? And that is where the complication starts, right? Do we draw, because, and from which class do we get that function, right? How does it know? Because remember, this is figure, right? If we call figure.center and then it calls draw, right? From which class? What do we want to draw here? Do we want to draw a circle, or do we want to draw? Do we want to draw a rectangle, or do we want to draw a circle, right? And that is where we start having complications. Okay, so now let's say we add a new figure, right? So let's add a triangle, and then it also derives from figure, and then we have the function center, which inherits from figure, right? And then now we need to understand, will it work for triangles, right? Because remember, the center function uses draw, right? Which is different for each figure. So then if we use, obviously then if we call the figure, like the center function from figure, then like we had this complication for drawing, right? But now in this case, let's say the triangle class then calls the function center, right? Because it inherited from figure. So now it's not figure who calls the function center, right? So when now we try to use the draw function, remember this is, it must be different for each figure, right? It will actually use figure draw. And that won't work for triangles, right? Because remember, when we created this function draw here, we did not know about triangles. We only knew about rectangles and circles, right? When we created this function initially, we did not know about triangles. We only created the triangle class at a later stage here, and we didn't know about it, right? So there's no implementation for a triangle in the figure draw class, right? So then when we call the center function, it will call the draw function, which will not work for triangles. And now we want the inherited function center to actually use triangle draw and not function figure draw, right? And this actually happens because of the fact that your compiler or our compiler does early binding, right? So let me try and actually explain this with code. So hopefully it makes more sense. So let's say I have a function. Let's say this function is, I don't know, center a figure, something like that, right? And then this function takes a figure pointer. Let's say it takes a figure pointer. And then remember, so let's say this function doesn't take any specific kind of figure, right? Its aim is to center a figure, right? So whether the figure is a circle, or it's a rectangle, or it's a triangle, this function will just do this. It will just say figure, draw, right? It will just, oh no, it will say center, right? It will just call that function here, right? But now, because the center function is not virtual in figure. Yes, so let's say this is a void function. So this is a void center figure, and then figure to center. And then let's say this is a center, so this is a figure class. So class figure. So let's create this class, remove the asterisk. And then this has a center function. Let's say this is also a void function. Right, and then here we have a draw function, right? That's called draw. And then let's say here's our draw function, void draw. And then this can draw, let's say like rectangles and circles because it doesn't know about triangles, right? And then here, then we have the center function, and then it calls the draw function, right? So even when I create a triangle, right? So create a triangle, and then so let's make it inherit from figure. Inherit from figure, and then so let's make it a public inheritance, and then obviously then I override center, right? Because I want so actually let's say I don't override this, but I only override the draw function, right? Because the center function, let's say it just takes the center points of any shape, and then it just calls this function draw. And then here, then I have a draw function. And then I override this. And then here, then I have my own triangle implementation of drawing, right? So triangle drawing code, something like that. All right. So now the problem is, this is not a virtual function, right? So as you can see, this is a void function, it's a normal function. And then here in main, so I create main, and then I create a figure, right? Because I want to pass the figure here, right? So I create a figure pointer, and then I say figure, and then I allocate memory for a triangle, right? Because I want to center the triangle and draw the triangle, right? So that is all nice and great. This looks fine on paper, right? When you look at it like this, right? It looks like this will allocate memory for an instance of a triangle, and then I will pass the triangle here, and then when I call this, it will actually call center. But then obviously when it calls center, then the draw function, it will use the triangle's draw function, right? But that is not true. That is not what's going to happen, right? When I pass this as a parameter, so when I call this function center figure, then what's going to happen is, obviously here, then I have this pointer, but what's going to happen is when I pass this as a parameter here, then when I call this function here, right, it's going to call the draw function from figure, not the draw function from triangle, right? And that is also like the concept of upcasting, right? Because that's actually what I'm doing here, right? I'm taking a triangle and then I'm converting it to a figure, right? And then because I'm taking a triangle and I'm converting it to a figure, then even though this pointer points to this memory location here, it will actually slice this triangle, right? So it will remove everything that is unique to a triangle, and then it will literally convert it to a figure, right? And then, so then when I call this function, it will no longer think about it as a triangle. It'll think about it as a general, like a normal figure, right? And then the figure obviously has its own draw function, and then that function will be called here. Right? So now, and that is the problem here, right? So even if I call the center function when I want to use it, triangle draw will not be called, right? But figure draw will be called, right? So it will use figure draw, right? And that won't work for triangles because remember, I added a triangle class at a later stage, and this draw function doesn't even know about a triangle. It only knows about circles and rectangles, right? So that is why this is a problem, right? So, so the class triangle wasn't even written when figure center was written, right? So basically, a figure doesn't know triangles, doesn't know anything about triangles, right? So then this is where virtual functions come in, right? So virtual functions are the answer to this, right? Because then a virtual function can tell the compiler that I don't know how the function is implemented, right? Wait until the function is used in the program. And then when the function is used in the program for the first time, then, sorry about that, get the implementation from the object instance. And this is the important part, right? You get the implementation from the object instance, right? So you wait until the function is called, and then you get the implementation from the object instance, right? That is the whole idea behind a virtual function, right? And this is called late binding or dynamic binding, right? And virtual functions implement late binding, right? So they bind the function's like name to an implementation at a later stage, right? So this is the same as, for example, then in this case, then I make this function virtual, right? So if I make this function virtual here, right, then this changes everything, right? Because then I'm telling the compiler that, okay, fine, there may be some code, right, that that implements, or rather that applies to rectangles and circles, and that is fine, right? But this function is virtual, which means that before you even think about using this implementation, wait up until you see when this function is called for the first time in code, right? Which obviously will be called through center because center calls it, right? So wait for the instance that calls center, and then choose the implementation that you will have, right? So then in that case, then what will happen is, so then because it's virtual, then when I create this instance here, so when I say new triangle here, right? When I create a pointer that points to this new triangle here, right? Then what will happen is, then so I have this pointer that points to this memory location, right? So even though upslicing happens, upcasting happens, sorry about that, upcasting happens, but because there's a virtual function here, right? When I call this, because there's a virtual keyword modifier, right? When I call this function, right? Then because the instance that this pointer is pointing to is a triangle, right? The center will be called in the context of a triangle, and then this draw function will then apply to this draw function in the context of a triangle, because this draw function is virtual, right? But if this was not virtual, then automatically the compiler was going to call this draw function, right? But when I make it virtual, then what I'm saying is wait till you see which instance is in context before you call this function, and then that is where that is when the compiler will then choose the appropriate draw function. Okay, so that is the whole idea behind a virtual function. So a normal function gets binded to its implementation before it's called, but a virtual function will get. Yes, that is correct. That is absolutely correct. Yes. Okay. Yep, this is cool stuff. Polymorphism is a very, very powerful feature. You learn about it more even like in second year when you do Java. It's very, very powerful. Okay, so here's another example. So a bigger example, yeah, so it's another example. So we have a record keeping program. Let me actually generate the code. Okay, I know it's not quarter past, but because I remember it now. Let's see, Friday, what's the date? 13, Friday the 13th code. Yeah. Okay, so if you're watching, that's the code. All right. So, so we have a record-keeping program for automotive parts, for an automotive parts store, and then we want to track sales, right? And then we don't know all the sales yet, but the only type of sales that we know are regular retail sales, right? So we know about retail sales. So we have a class called retail sale, and that's the kind of sale we know about, right? And then, so we don't know about discount sales, we don't know about mail order sales, etc. Right? So we only know about only these kinds of sales, right? And so remember, discount sales, for example, depend on other factors besides just price and tax, like value-added tax and so on, right? We have to consider like discounts, what's the percentage of the discounts and so forth, right? So when you calculate the bill based on this sale, we are going to calculate it differently than when we calculate like a regular resale sale, right? And then also like with mail order sales, there are other factors to consider, right? So then the program must compute daily gross sales, right? So, and then we need to also calculate the largest or smallest sales like of the day, and then we need to calculate the average sale of the day, right? So, and all these come from individual bills, right? And so, but now there are many functions for computing bills, and they will be added later, right? When different types of sales are added, right? Sorry about that. So the function for computing a bill then will be virtual, right? Because we don't know what will be added later, right? Because obviously here we have different types of sales. So for example, this sale will have like a compute bill, right? Function. But then a discount sale will have also a different compute bill function, right? And they won't function the same way, right? So then what we do is we create a sale, and then what we do is we add a function, compute bill, and then we make this function virtual, right? So say it returns a double. So then, and then if, for example, we don't know, right? So if there's no default way of completing a bill, right? So if it will only depend on the kind of sale, then we make it a pure virtual function, right? And a pure virtual function will mean that in the parent class, there will be no implementation. So this is not allowed for a pure virtual function, right? We can't have an implementation in the parent class, right? It means that we can only have an implementation in the derived classes, right? So this will inherit from sale, and this will also inherit from sale, right? And then these will then provide the implementation for computing the bill, right? So that is the whole idea behind virtual function, right? And then when you add another type of sale 10 years later on, then you can just add that sale, so mail order sale, and then that also inherits from sale. And then all you do is then you just continue, and then you add your own compute bill function, and then that is that, right? And then this is the essence of polymorphism, right? So it means that this function can behave in different ways, right? Or has different meanings, right? Based on how you are using it, right? So if you're using it in the context of a retail sale, it has a different meaning. If you're using it in the context of a discount sale, it has a different meaning. If you're using it in the context of a mail order sale, it has a different meaning, right? So that's the whole idea behind polymorphism. Okay, so here's the code. So this will probably not look like the code I just wrote. I actually didn't. Yeah. But it's the same idea. So you have a class sale, and then it has a bill, and then so it's a const because it's not allowed to change the price. It's only allowed to calculate the bill. And then, so as you can see here, it's also not a pure virtual function, which means that it probably has like some sort of, like defaults implementation. And then, so you have a savings function, which basically takes another sale, and then it just checks how much you saved, right? So it will take the other sale, then it will calculate this bill minus the bill from the other sale, and then that would tell you how much you saved. And then so the class sale represents sales of a single item with no added discounts or charges, right? So then the reserved word virtual in the declaration member function bill, right? And the impact that it will have is that the derived classes of sale can then define their own version of the function bill, right? And then other member functions of sale will use the version based on the object of the derived class, right? So that is the whole idea, right? So remember, in this case, for example, we have the savings member function, right? So it will use the bill function based on the type of sale that we have, whether it's a retail sale or a mail order sale. Okay. So then we have a discount sale, and then here's our complete implementation of the bill function. And then, so now this obviously does its own calculation of the bill. And then, so in the function definition, then you don't have the virtual qualifier, right? So if you remember from your tutorials, you have a virtual qualifier only in the header file, but in the CPP file, you don't have the virtual keyword. So, and then, so it's automatically virtual in the derived class, right? So you don't have to specifically provide it there. And then, also in the header file, you don't really required to have the virtual keyword, but usually you will have it just to show that it's a virtual keyword, it's a virtual function, but you don't have to have it, right? As you can see here in this header file, there's no virtual keyword. And then, but in the CPP file, usually you don't have, you're not allowed, you get a compiler error if you include the virtual keyword. Okay, and then so then the virtual function in the base class is automatically virtual in the derived class, and the derived class declaration is not required to have the virtual keyword, so I just mentioned that. But typically we include it anyway for readability, right? To show that this is the function that like this function is virtual, right? So, but I don't usually include it in my code, but I know like other programmers, for example, do include it. So it's really up to you, right? But I do believe that if you include it, it doesn't hurt. It actually does improve the readability of your code. Okay, so, and then, so the discount sales member function bill will be implemented differently than the sales, particular to discounts, right? Because so this will be the function in the sales in the discount sale class, right? So this is the function, right? So it's differently from the original function, which actually they didn't show us the implementation in the parent class. Okay, so, and then, so in terms of the member function savings, so this savings function, so if you remember, this function uses the bill function, right? But now, because the bill function was made virtual here, this bill function, right, the compiler will wait until it knows what instance exists in memory, right? So if it's a discount sale instance, then it will call the bill function of the discount sale instance. All right, yeah, so the late attendance code was posted. But remember, you don't have to fill it in if you're already in class. It's only for students who were not able to attend the live lecture. All right, and then yeah, so when you call this function, then it will call the virtual, or rather it will call the bull function based on the instance that you allocated memory for. If you allocated memory for a discount cell, as in our initial example, then it will call the bull function of the discount cell. So instead of defaulting to the version defined in the cells class, right? So that's the difference between just having a normal function that's, for example, overridden like via inheritance, and actually having a virtual function, right? So it's exactly what we're explaining in terms of the figure, right? So if it's just like this, then it will default, right, to the version defined in the parent class, right? But then if it's virtual, it won't default. It will wait up until it sees which instance memory was allocated for. Okay, and then okay, so yeah, virtual functions a big deal, and then so yeah, so actually this is pretty amazing. This is like a really powerful feature, like in terms of object orientation, because it means that you can create it, like you can create a class, right? The soul class was created a long time ago, right? So it can be written long before the derived class, right? And then at some point when you create the derived class, because there's like the function in the parent class is virtual, right? Then all you need to do is basically just redefine that function, right? And then that function can be called, right? So this is also known as future proofing in programming, right? It means that you can create a class now, and then you can create functionality for the class, but then you don't have to worry about backwards compatibility, right? In the sense that every time you create a derived class, now you have to go back to the parent class and then add some code that will support the derived class, right? Because that is backwards compatibility, right? But this is future proofing. It means that you don't have to worry about it in the future. You can create that function now, and then all future, like derived classes, different kinds of derived classes can then have their own implementations of that function. And the compiler will know which implementation to call based on the memory that you allocate, because then you allocate memory for the instance that you want. All right. So members savings and that. Okay, I actually didn't see a function like that in the code. Let's go look for it. Yeah, so there's only the savings function. Yeah, okay. I think that might have been a mistake in the slides. But the point is this function here, right? The savings function was also compiled before, right? There were even ideas of a discount sale class, right? So we didn't even know that there would be a class which would exist in the future called discount sales, but we were able to provide some future proofing for it. Okay, so so in a call like, so we have discount sale, D1 and D2, and then if we say D1.savings, and then we provide D2, the call in savings to the function bill will know that it needs to use the definition of bill from the discount sale class, right? So that's the powerful feature about virtual functions and polymorphism. Okay, so I think I'll stop here. Yeah, I think I'll stop here, and then because we're almost out of time, and then yeah, so I think Prof. Pulse will then continue from the next slide. But let's just look for questions. Okay, so there's no questions. All right, so thank you very much for your time, and do enjoy the rest of your day. And don't forget, we do have practical sessions, and the next practical will be released during the practical session. And remember, when you attend the practical session, you also have the opportunity to ask questions. both, like to lecturers and assistants, and you can also query the practical mark, like for your previous practical assignment. So please attend practical sessions, very important and very informative. But thank you very much for your time, and see you guys next week or in the practice.